All right, this is a YouTube video talking about calculating pH for simple buffers. And I'm going to begin with the Henderson-Hasselbalch equation, which relates the pH to the pKa plus the log of the weak base concentration over the weak acid concentration. And these brackets indicate that these are actual concentrations, although in practice we often use formal concentrations, or the analytical concentration of the weak base and the analytical concentration of the weak acid. So let's go through and do a problem. We'll begin by assuming that our buffer pKa is 6. The Ka is computed below that, and we're going to use 10 millimolar total weak acid and total weak base. And if we, again, assume that A minus and HA are equal to the formal concentrations of total acid and total base, cell B50 is the Henderson-Hasselbalch equation, and we get an answer of 6, which makes sense. A over HA ratio is 1, log of 1, 0, pKa equals the pH, or pH equals the pKa. Now the assumption that the concentrations of the base and the acid are equal to the formal concentrations are very good for buffers with concentrations over 10 millimolar, and often buffers with concentrations over 1 millimolar, as long as the pKa is above 3 and below 11. But as you move towards stronger weak acids and stronger weak bases, the computed pH, in this case, let's make it stronger, as in P2, the computed pH by our sort of simple-minded approach would be 2. And in this case, the H plus concentration will be 10 to the minus 2, or 10 millimolar. And the problem is, where do those protons come from? Well, the protons have to come from the dissociation of the weak acid. And if they come from the dissociation of the weak acid, you don't know the HA concentration anymore. It is no longer equal to the formal concentration. So the solution to this problem is to do careful mass balance and charge balance. And when you do this, you get a better expression for the Ka, which accounts for the gain of base from the H plus dissociation, or the weak acid dissociation, and the loss of weak acid from the weak acid dissociation. So this expression can now be solved using the quadratic, where the A term is 1, the B term is the total weak base plus the Ka, and the C term is the negative Ka times the total weak acid concentration. So that's what I've done in cell B51. B51 is the quadratic equation solved in terms of H plus, using the A, B, and C terms, which are a function of the analytical concentrations of the weak acid and the weak base, but correcting for the fact that the H plus concentration must come from the dissociation of the weak acid. And so when you do that, you notice that the pH in this exact solution is 2.38, and so it's significantly higher than what you would calculate, and this again counts for the dissociation of the weak acid, producing now a lower concentration of H plus, and the buffer having a higher pH. We can change this to pH 3 or pKa of 3, and you see these become quite close. And by the time we get to pKa of 4, the difference between the simple and exacts are small, because the proton concentration is now 1/10 of a millimolar, and it's a very good approximation that the total weak acid and total weak base equal the A minus and HA concentration.